It stressed me out.
I've got a test in another subject today.
I also have to finish the rear card. It's our own company.
That's the part of the life, right?
Yeah.
That's the game.
Touche, only touche. They tell me, why do you want this job? I want to make money. And it's like, well, why? Are you happy? Like, no, I just need to eat.
Gotta eat to live, right?
Yeah.
Okay, so I think you hope you did well in your exam. Is that right?
That's the hope. That's the hope.
Okay, I haven't seen the grades so far, so I don't have any comments about your performance until now. So I am sure that you all did very well.
I feel pretty good about, in my case.
That's very good. Because the questions were, most of them were very straightforward. Almost all of them were very straightforward. You have solved similar problems. Either we have solved in the class or in the homework, right? And the questions were discussed. So there is no way you can complain, I assume. Agree? Agree. Okay. Something going on with these lights.
I am noticing that the lights keep getting brighter and dimmer. That
I don't
isn't
know what's
you.
going on.
This motion. No, seriously. Someone talk about motion.
Motion is there?
Yeah.
There is no option anywhere.
He's just talking about the test, and then the lights went on.
I don't know how to do that, I don't see any option anywhere here to change anything. So,
See how it goes here. Oh.
this is the problem from the chapter 4. It's a very simple problem. I assume that I don't need to solve it in the class. Is what is the composition in weight percent of an alloy that consists of 6 atom percent of lead and 94 atom percent of tin? Atomic weight of lead and tin are 207.2 and 118.71 grams per mole respectively. So the equation to solve, I am not going to solve it, this is very simple. C1 dash A1 over C1 dash A1 plus C1 prime A1 over C1 prime A1 plus C2 prime A2. And just substitute the value. Very straightforward question. So you can do it. You have all the atom percent here of an alloy consists of 6 atom percent of lead and 94 atom percent tin. So atom percent C1 prime is 6 atom percent and C2 prime is 94 atom percent. So atomic weight of lead and tin are 207.2 and 118.71. So A1 is 207.2 and A2 is 118.71 grams per mole. Just substitute those values there and solve it. Okay, it's very straightforward. So I assume that you don't want me to solve it here. So the next one is, I think you solved one problem from here in your homework, but some hypothetical alloy is composed of 12.5 weight percent of metal A and 87.5 weight percent of metal B. If the densities of metals A and B are 4.27 and 6.35 grams per centimeter cube respectively, whereas their respective atomic weights are 61.4 and 125.7 grams per mole. Determine whether the crystal structure for this alloy is simple cubic, face-centered cubic or body-centered cubic. Assume a unit edge length of 0.395 nanometer. So you are asked to determine the average, if the densities of A and B are this one, whereas that way determine whether the crystal structure for this alloy is simple cubic, a simple cubic, face-centered cubic or body-centered cubic, FCC, BCC or simple cube. How can you do that? So what is the equation? We have an equation, you remember the equation to determine the density rho is equal to N into A over
And so the A times the volume.
BC into
Avogadro's number.
Avogadro. Okay, so if you determine this one, N from here, okay, so you should be able to tell whether it is simple cube, face-centered cube or a body-centered cube, right? If n is equal to 1, simple cube, n is equal to 2, it is body-centered cubic structure, and n is equal to 4, it is a face-centered cubic structure. So, but the problem here is it is an alloy. What we have learned is only about a single element A or B. It is not an alloy. The equation is for a simple element, a single element A or B or whatever. So how can we do this one? You need to solve it based on the average, right?
Yeah, you solve for both and take the average.
Yes. So you need to take the row average, okay, and then another one you need to determine is a atomic weight average. Okay, atomic weight average. So once you have this one, we can rewrite this equation. Rho average is equal to NA average over BC into NA. Okay. So, but how can you determine BC? Because the radius is given. So edge length is given. A is given, right? So the BC is, we can easily do BC. What is that one? This is AQ. So we can write it as rho average is equal to NA average over AQ into NA. So now we know what is the equation to determine rho average. Rho average is equal to 100 over C1 over rho1 plus C2 over rho2. And A average, the equation is A average is equal to 100 over C1 over A1 plus C2 over A2. Okay, now you can substitute all these values. Okay, for C1 and rho1, you know what is C1, right? C1 is equal to 12.58%. C2 is 87.58%. And if the density is rho1 is equal to 4.27 and grams per centimeter cube, and rho2 is 6.35 grams per centimeter cube. Atomic weights. Atomic weights A1 A1 is A1 is equal to 61.4 grams per mole, and A2 is 125.7 grams per mole. Now you can do it at home, right? Just substitute those values and solve for that for n. Okay, n is equal to rho average into a cube into n a over a average. Okay. Here you will get for this one, this particular question, the answer, the n is about 2. It is 2 atoms per unit cell of the alloy. Okay? So, what type of crystal structure is this?
That is a body-centered cube.
Body-centered cube structure. This is the structure. Okay, I think that's it. And we finished the other one, right? The other chapter, right? Almost everything you assume we finished it from there. Yeah, this is the one which we were talking about last. So this is the linear intercept method for the grain size determination. There are two methods. One is the linear intercept method and the other one is the comparison method. So what is the linear intercept method? You draw a line across this one, this grains, and look at the number of grains intersecting that line. And then you know what is the total length of that line with a given magnification. Then you can mean intercept length can be determined from this equation. LT, that is the total length of lines, over P is the total number of intersections, and M is the magnification. Second method is comparison method. What is based on the comparison method? Comparison method ASTM. ASTM, they have a lot of standards. I will come back to the ASTM standards in the coming chapters. Okay, what is ASTM? You must know what is ASTM and all. But for the time being, you have a number of standards there. Okay, and but that is the micrographs of several samples with different grain structures. And they have assigned a number from 1 to 10. With a magnification of 100. Magnification is 100, and you are assigned a number with a number of micrographs with these numbers. Now you are given a certain sample. You need to determine under a certain magnification. You take the image, that the micrograph of that sample. Now compare it with the sample given in the ASTM standard. Okay, and see your sample matches with the which sample. For example, if your sample matches with the fifth, size number 5, then you should give that number here, that is G and N be the average number of grains per square inch at a magnification of 100x, then G and N, that grain size number, is 5 here. Okay, that 5 here, and the G represents, sorry, it's not 5, the G represents the grain size number, so it is the 5 is here, 5 minus 1, and n be the average number of grains per square inch. These two are related by this equation. N is equal to average number of grains per square inch, and the grain size number, these two can be related by this equation. N is equal to 2g minus 2 to the power g minus 1. Okay? I think that's it. This is just for your information. You need to know that there are ASTM standards, and if you get a given sample, for example, you will deal with a lot of steel in the future, and if the number of there are numbers, steels are represented in terms of numbers. Okay, that number matches with the given number of ASTM standard. And then if you want to calculate the average number of grains per square inch, then you can use this equation. Okay, so this is basically because all these grains are look at these things, the shapes are not the same, right? They have various shapes, different shapes. So that's the reason why we use this standard. So let's go to the next chapter. So next chapter is diffusion, and this is a very important chapter, diffusion, and diffusion takes place in materials, and what we are going to see is what is diffusion and why it is important for part of processing. How can diffusion rate be predicted from some simple case, and how does diffusion affect the temperature affects the diffusion? So what is diffusion? You all know what is diffusion. For example, if I open a perfume bottle here, in a few seconds time, those who are sitting there at the back, they can smell it. Agree? Agree? Because there is a diffusion of these atoms of that perfume from this part to that part. So another example, if you add a drop of ink into a bottle, okay, and you can see that that ink is dispersing into that whole solute water, into the whole water volume, right? So again, it moves from one part to another part. We were considering one, the gas, the perfume, second, so solution. But the same thing can happen in solid too. Diffusion of atoms in solids. So what is the diffusion process? Diffusion process, I said, okay, I open the bottle here, the atoms move from this point to the another point. Therefore, we can say that it is the movement of the material, matter. Or atoms, when you come to that microscopic level, it is the atoms, but the movement of that atoms or matter from one point to the another point. Agree? And I said that, can you smell that, if you are sitting somewhere there, can you smell at the same time, that is the same moment I open it, somewhere there, if you are sitting somewhere there, can you, we are talking in terms of maybe in the fraction of a second or in seconds. There is a time lag between here and there, right? So we can say that it is a time dependent process too. Yes?
Wouldn't you need wind though? Wind?
Yeah. Wind, that is another force which we do not consider here. Okay? Wind is, of course, what you're saying is correct. If there is wind, it is going to faster that movement of atoms. But we consider there is no movement like that one. We consider only, for example, here without no AC current or anything like that. That is the movement of the atoms or particles. Agreed? And what drives that movement? What drives the movement of atoms from here to here, there? Or in a bottle of water, glass of water, what drives the movement of that ink atoms from wherever you drop to another part of that one? Yes.
Basically it has to do with the vibrations of the atoms and molecules that make up the
Yeah, I agree. That is the movement, right?
yes.
You're talking about the movement. Yes, movement. What drives that movement? That is my question. Yes. Degrees of freedom. That is the it's free energy and all those things. It's not a very straightforward answer. There is a straightforward answer. Degrees of freedom. That is the randomness and all those things. The free energy. We are not considering any of those things here. It's a very simple thing. So at the top of that bottle there is ink, and but somewhere at the bottom or maybe on the side there is no ink. So what is different in these two cases? Or perfume. I have perfume here and no perfume over there. Yes.
The concentration gradient.
Absolutely. Concentration gradient, very important term. Diffusion is driven by the concentration gradient. That is the difference in the concentration between two parts of a system. Okay, that is the concentration gradient. So we talked about it. There is a, it depends on the atoms or matter. Matter moves from one point to another point, and there should be a driving force. There should be a driving force for the atoms to move from one point to another point. And the driving force in this case, in the case of diffusion, is the concentration gradient. Difference in the concentration between the different parts of your material. Okay, so it is a time-dependent process, and it is a concentration-dependent process. And again, what else? It depends on if you have a very heavy atom and a lighter atom. Heavy atom and a lighter atom. Which one moves faster, diffuse faster to that side?
A lighter atom.
Lighter one. So the property of the diffusing species is also important. Agreed? The property of the diffusing species is important. Now you consider that it's a very dense gas here. Very dense gas. That is the medium. You are opening the perfume on this side, but there is a dense gas here. So whether it's going to be easy for this atom to diffuse to that point, or whether it is difficult when you have much denser medium here in between. Well, is it easy or difficult for this ion?
Depends on the
Difficult.
pressure.
Difficult, right? So which means that the medium through which these atoms diffuse, that is also important. Agree? The medium through that diffusion happens. The diffusing atom is your perfume atoms, and the medium is the air here. So that air is important as well as diffusing species is important. So what's the point I am trying to make here? So when you have an alloy or a material, okay, solid material, and you want to diffuse another element or metal through that one. Okay, mostly we are talking in terms of solid state diffusion, but and what are the important parameters you need to consider? What is the atom that is diffusing, and what is the medium through which it is diffusing? And there are so many other conditions too, like temperature is another important factor. Okay, temperature is another important factor. So now consider a material with a lot of defects and not that much defects in your system. And you are considering an atom that is diffusing through that medium. Okay, one with a lot of high number of defects and another one with a low number of defects, even if it is the same material. Which one diffuses the diffusing species through that one easily?
The one with the one that is pure, the one with fewer impurities will diffuse more easily because
Diffuse the diffusing atoms easily. Okay, any other answer? Think about it. Yeah, please think about it. Ones with the looser bonds, and which means
that they have a higher energy.
in terms of defects. That's what.
Yeah.
Yeah, come on, you guys come. Just think about it. You have one sample one with a lot of defects and sample two without any defects. Which one diffuse the diffusing species? That is diffusing species if it is A and the medium is B. Which one diffuse? One is B1 and the other one is B2. B1 has more defects, B2 has less defects. My question is, which one, whether B1 or B2 diffuses atom A easily through which? Is it clear? Is the question clear? Come on, say something.
It diffuses to the one that has more defects.
Absolutely. Yeah. One with the more defects, that will diffuse this atom A easily. Because think about it, we can just consider one with the defects. You know, if you are moving through these chairs to that point, you know, there is no way like this one. You are moving through that one. Okay? You have only considered this much chairs here. I want to go straight from here to there, not through that ramp here. So, but in one case, I have some of the defects here. That means some of the chairs are not there, are absent. I can easily go through the space if you have that defects here, right? Without any chair. But if it is defect free, I need to jump from one point to the other point to the other point. It is harder. Do you agree? Same thing. Same thing. So that's the point. Now, let us consider. We have already talked about most of these things. Diffusion, it is that so it is the mass transport of atomic motion. You agree?
yeah.
Then movement of particles from high concentration to a low concentration. What is that?
The concentration gradient.
gradient. Remember these things. This is important. Concentration gradient. From high concentration to a low concentration. That is the concentration gradient. And the mechanism, gases and liquids, is random motion of atoms from one point to another point. Whereas for solids, vacancy diffusion or interstitial diffusion, which we are going to see next.
Hold on. Since you're not writing, we're like it's taking us a little bit longer since you haven't typed now.
Yeah, so I will upload the other slides.
Can you upload the finished ones?
But don't the reason why I'm still showing it is please write it down with me.
Yeah, but it takes us a little bit longer.
Yeah, sure, go ahead.
Sorry.
It's okay. Don't worry, I will upload the slide so you can get it from there. So, interdiffusion. What is the interdiffusion? If this is a single element itself, or it can be it can be two metals, metal A and metal B. You can consider it as metal A and B also. And this is the interface of this metal A and metal B. You are joining two, metallurgically joining two metals. Okay? These two metals are joined together. So what you can see after some time, initially it is everything, this is 100% here and this is 100% here. What happens after some time is, you can see the atoms of element A diffuses into element B, and atoms of element B diffuses into element A. That is interdiffusion. Interdiffusion of atoms. So if you look at the concentration profile, you have it initially, it is completely, this side is completely, you see this side is completely element A, and the second side is completely element B. But with the time, you see the concentration changes at the interface. So this is just to give you the idea that these type of atomic diffusion can take place even in solids. Okay, that is the solid state diffusion. So this is also a very important parameter. I teach this in this type of solid diffusion in higher classes. What are the important things we need to look at the solid state diffusion and the kinetics of that one. So what is the time dependent process? Kinetics means time dependent process of that diffusion. But there can be self diffusion too. For example, if you label a certain atom A here, A and C, after some time we can see that same A changes location from here, this point to another point, and the C is moved from this point to another point. This is just to show you that even if it is it's the same element, atoms can diffuse from one point to another point. Just to get that message. So what are the different types of diffusion? It is a stepwise migration of atoms from lattice to lattice site. You see, vacancy diffusion is something like this, and you can see that if there is a vacancy here on element B, okay, this is a vacancy here at the intersection of the element B. What can happen in this case? This atom can move from this point to this point, and once that vacancy is generated here, an atom from here can move here, or from here it can move here, and for here it can move here, right? A vacancy is generated basically because this atom moved from here, this point to this point. Okay, you see, now it is moved to this point, and a vacancy is generated. Another atom can move to this point. For example, if this moves to this point, you see this atom in this case can move to this point, and further diffusion can take place. That is called the vacancy diffusion. Okay, vacancy diffusion. So remember, in this case, it's not that easy to move from one point to another point, because it needs to have certain energy to move from one point to another point. Yes.
Is that also considered a self-diffusion?
Yes.
Yes.
So this is a interdiffusion. Self-diffusion means if it is only element A. Atoms of element A can move from one point to another point. But here in this case we consider just the A and B. And at the intersection, if there is a vacancy, A can move to that vacancy. But there are number of factors there, right? For the B, whether if they are of a similar material. Agree? So, what about, consider this one, the chairs you have there. Imagine that you are sitting here on this, here in this chair. So you want to move to a vacancy, if you decided, oh, I'm very close to, you are very close to me, I want to move to that point. What you need to do, imagine there are no ramp here or anything like that. What you need to do, you need to again get up, jump from here to there. Agree? Are you getting it?
Yes.
So, what you need in that case?
Energy.
Energy.
And also in this particular case, skill and carefulness.
Absolutely, all the substrate or the medium and the diffusing atom, they are all important. So you need an activation energy. Agree? You need an activation energy to jump from this point to another point. So only if you have that much energy, you can move from this point to another point. So remember that, we will come back to that one. So only that condition. So typically you can get it from the temperature. Agree? Temperature, if the temperature is high, the atoms can get more energy and it can move from one point to another, which is the activation energy. So as the time elapses, as the time increases, you can see that this type of movement occurs in material. Another important thing is the interstitial diffusion. What is interstitial diffusion? Again, if there is some space in between these chairs, and if it is a baby, for example, if it is a baby, then the baby can maybe able to squeeze between the chairs to that point. Agree? Squeeze between the chairs. So that is called interstitial, because there is a separation, small separation between these chairs, and if you can squeeze between these two chairs and move to the interstitial space, the space in between, that is called the interstitial diffusion. Very clear? So, a very good example for interstitial diffusion is the preparation of steel. What is steel? Basic steel is carbon diffused in iron, where the carbon atoms are much smaller than iron atoms. Therefore, this interstitial diffusion can take place there. So this is exactly what is shown here. One atom diffuses through the interstitial space to another atom, and this is interstitial diffusion is much faster than substitutional diffusion. Agree? It is much faster than substitutional diffusion. A very important example is the case hardening. Case hardening. Case hardening is a case where you have this gear made up of steel, okay, and a certain steel, and what you do is you diffuse more steel into the outer surface of this this gear. Why? To make it harder. Okay, to make that outer surface, this surface harder, what you need to do is you need to diffuse more carbon into that steel. So that is a very good example of that case hardening. So again, we will learn more about this case hardening later on. Okay, but you need to remember it is an example of interstitial diffusion. So the presence of more carbon atom. So it makes the steel harder. Okay, it makes the steel harder. So that's an example, case hardening quiz question. Okay, so you can make the gear more harder, or outside of the gear harder by diffusing more carbon atoms into the steel. Another very good example is the development of semiconductors, ICs, integrated circuits. What is a semiconductor? From your high school classes, or maybe even some physics class, a semiconductor is one with a conductivity in between a conductor and a non-conductor. And in ICs, you need to have, for example, you dope 4 group elements. Okay, 4 group elements, silicon is a 4th group element, with the other groups like a 5th group or 3rd group. 3rd group or 5th group. And if you dope the silicon with the 5th group element, you can get an N-type semiconductor. And if you dope the silicon with the 3rd group element, like boron, you can get a P-type semiconductor. Okay, either 5th group element like phosphorus, dope it into silicon, you can get an N-type, an excess of electron, that is the N-type semiconductor. But for the P-type semiconductor, you need to dope it with the 4th group element. So, why it is important? Your semiconductivity, the conductivity depends on the number of dopants you have in silicon. So, it must be very precisely controlled. Okay, it must be, the dopant concentration should be precisely controlled to get certain properties of that semiconductor, which is also important. And you can see that ICs are everywhere, right? It's everywhere. You can see that integrated circuits and semiconductors. So you need to have a very precise concentration of this one. And there is the precise level of this preparation of dopants in silicon, and the formation of a silicon oxide layer on top of it to make a semiconductor and a transistor, that led to the development of company Intel. Intel was based on that invention. Okay, so you can see how important it is. Okay, how important that preparation of semiconductor is, precisely control the semiconductor. So they developed, I forgot the name of those people, but they developed a technique to develop this one and another silicon dioxide coating on the surface so that no diffusion into the outside can happen, and that led to the development of the ICs and Intel, and that was the patent $1 billion or maybe even $1 trillion patent developed at that time, right? At that time, now the companies, so many companies are developing it. So the importance is you see, look at this one. This is the deposition, either phosphorus or boron or whatever type you want the atom to be diffused into silicon, and at the precise locations you put these materials, these atoms, and it can, at a certain given condition, the temperature and pressure and all those conditions, you can diffuse these atoms into silicon and you can make a semiconductor. Okay, so that is the importance of diffusion. So now you need to come across a term called flux. Again, what is flux? Flux is nothing but, if you have, imagine that you have only one door there. Okay, one door to this classroom, you don't have the other door. So you can see that it opens right at 10:30 when our class starts, And what you need to know, all you guys need to come into this one. But if there are more than one door, you don't need to rush that much. Agreed? So flux is nothing but the number of students entering into the class per unit area. The door is the unit area. Agreed? Door is the unit area per unit time. That's the reason at 10:30, you need to enter in within a minute or so. So that is the flux. That is, the flux is the rate at which mass, in this case, you guys, the mass of you guys, the students, mass of students, mass, charge or energy. Okay, in general flux, flux is this one, but for diffusion it is the mass transport. Okay, this flux is in general terms. It can be mass, charge or energy traversing through a unit area in a given time. That is the flux. For diffusion, what is it? The number of atoms. Agreed? Mass of the atoms passing through unit area, unit cross section or unit area of a given material in unit time. Do you agree? So that's how we can define it. Diffusion, J is equal to the flux. Diffusion flux is equal to moles of diffusing mass of the diffusing species per surface area in unit time. In unit area in unit time. So we can say that it is mole per centimeter square per second. Agreed? Mole is the quantity. Mole is the quantity. So mole is the quantity, or mass can be expressed in kilograms per unit area in centimeter square. Area in centimeter square in per unit second. Unit time. So, or it can be kilogram per meter square second. So, it can be measured empirically, and that is you can make a cross-sectional area, a thin film of non-surface area, non-surface area, and then what you need, a very important aspect, there should be for diffusion to happen, there should be a concentration gradient. Concentration gradient. So only if there is a difference in the concentration between the two parts of your system, then this diffusion can happen, and then you can measure the flow of atom. Measure the flow of atoms through your medium. So we can write it as J is equal to, that is the mass transported per unit area in unit time, or we can say it is 1 over A into, you can get the differential dm over dt. So we can, diffusion flux is the mass of the diffusing through and perpendicular to the unit cross-sectional area in a solid per unit time. Diffusing through perpendicular to that medium. Okay, it is the mass of the atoms diffusing through and perpendicular to the unit cross-sectional area of solid per unit time. That is the diffusion. Now there is something called a steady state diffusion. Okay, steady state diffusion, again it's important what is steady state diffusion, and there is another one coming, non-steady state diffusion, you will see in the next slides. The steady state diffusion is something like this one. here? You have a chamber. Assume that you have a chamber. And if this chamber is separated by a membrane, okay, a separator through which you want the atoms to diffuse. Are you getting it? This is a chamber, and this chamber has been separated with a material through which you want your atoms to diffuse. Got it? And in order for the diffusion to take place, what should be the driving force? Concentration gradient. There should be difference in the concentration. So there should be a flow of atoms from high concentration to the low concentration. So what is the condition? Pressure, gas pressure. If you are diffusing a gas, the gas pressure should be high on this side and gas pressure should be low on the other side. Agreed? That is concentration gradient. So far so good? Okay. So this is a thin medium. Now it is diffusing through that medium. Atoms diffuse through that medium. And at some point, you can see that number of atoms. Imagine like this: if there is a lot of students on this side and fewer students on this side, the number of students entering from this side is same as the number of students exiting through that door. Okay, entering and exiting. If the number of atoms entering is equal to the number of atoms exiting through this door, then we can say that a steady state is reached. Okay, I will repeat it again. Okay, here you have a diffusing species and a diffusing medium, and you keep, if this is a chamber, you keep the pressure on one side at a certain pressure, and it is kept constant. That pressure is kept constant, and this side there is another pressure, and that pressure is kept constant. And the condition is pressure on this side is higher than the pressure on this side. When you can say that a steady state is reached once the number of atoms removed from this, diffused out from this medium, is equal to the number of atoms entering into the chamber from this side, or entering from this side is equal to that one. So which means, what is the meaning of that one? So you have that medium, there is no accumulation. Once the steady state is reached, there is no accumulation of atoms within that medium. Agreed? Agreed? So that is called the steady state diffusion. Once that condition is reached, you can say that a steady state is reached. Any question? So that is represented here. You see gas at pressure PA and gas at pressure PB. You assume that okay, this is a medium and it is a chamber, there is no diffusion through the top and all those things like what I said. So gas at pressure A and pressure B, PA is greater than PB and constant. And this is a thin metal plate with a given area and with a given thickness. This is considered as X, the thickness of that one. Okay, the thickness of that medium, diffusing medium, and you can write it as, here you see this is the concentration of the diffusing species and the position X, and when you plot the concentration versus the position X, this is the position X, you can see that you can get a line like this. Once the steady state is reached, if linear, then we can say that dC by dx. Okay, what is dC? The change in concentration. Okay, change in concentration over change of distance. That is the thickness. Is equal to, that is delta C over delta X is equal to Ca minus Cb, that is the concentration of atoms, concentration of that species on this side at a higher concentration side, minus the concentration of species at a lower concentration side, Ca minus Cb over Xa minus Xp. That is the X. What is Xa? That is, this is Xa minus Xb is the thickness of that diffusing species. Okay, so this is the equation. dC by dx is equal to change in concentration over change in distance. So we can write it as Fick's first law. Again, this is important. Fick's first law is important. Rate of diffusion in this case for the steady state diffusion. Once the steady state is reached, is there any change with respect to change of concentration of the diffusing species through this medium with respect to time?
No.
No. Very good. There is no change in the concentration once the steady state is reached. Okay? Once the steady state is reached, there is no change in the concentration with respect to time, and that's the whole reason why we say that it is the steady state. So we can write it as the Fick's first law, that J, what is J? Flux is equal to minus D into dC by dx. Okay, and D is a coupling coefficient, okay, which is called diffusion coefficient. Okay, this is D is the diffusion coefficient, and you know, this is a coupling constant. Why it is called a coupling constant? It is a coupling coefficient. This is a coupling coefficient that connects, couple between flux and concentration gradient. And D quantifies the ability of a species to respond to a given force with the movement as well as the effective strength of the driving force. So D depends on the ability of that material. We have this material, right? That is the diffusivity of that material. Okay, depends on what it is the that depends on that given material itself. For example, if you are making a steel, D depends on the iron itself, right? What type of iron you have, whether you have a BCC structure or XCC structure or whatever structure you have. And again, it depends on the concentration gradient of the diffusing species, and so force of the movement as well as strength of the driving force. Strength of the driving force is that concentration gradient. Okay, so we can write it as J is equal to minus. Okay, minus. Remember, it is minus of D into dC by dx. This minus sign is basically because the flow of atoms is from high concentration to low concentration. That is the reason why there is a minus sign there. Minus D into dC by dx. So D depends on the property of the species that is moving and material through which it is moving. So we can get it C2 minus dC by dx. When the steady state is reached, you can say that dC by dx is equal to delta C over delta x, which is the change in concentration, C2 minus C1 over X2 minus X1. Consider the concentration on this side as C1 and concentration on the other side as C2. And if this location is X1 here and X2, we can write it as difference in the concentration, C2 minus C1 or C1 minus C2, that is the difference. You are considering only the difference. Either it can be C2 minus C1 or C1 minus C2 over X2 minus X1. That is the dC by dx, concentration gradient. So this is just the units. So J is flux is number of atoms per meter square second is equal to minus D in meter square per second into dc by dx, which is the number of dc is the concentration, so number of atoms over m cube into 1 by m. Okay, so concentration atoms per meter cube into 1 by x because of the dx there. So you can get this as atoms per meter square second. That is the unit of flux. So diffusion coefficient depends on the certain factors. One, which is the diffusion mechanism. Agree? Whether it is interstitial or substitutional or whatever the mechanism of transport. That is the interstitial, the diffusion mechanism to temperature. We will come back to this one, temperature. You remember, whenever the temperature increases, what happens to that diffusion? It increases. It's very simple, right? The vibration increases and the transport also increases as the temperature increases. So temperature is another factor. And what is the third factor? The crystal structure. So why crystal structure is important? Packing factor, we learned about packing factor, right?
Yeah.
So what is the packing factor of FCC?
0.74.
0.74. What is the packing factor of BCC?
0.68.
Yeah, so it can be different. Again, depending on the materials and all those things, but these are the crystal structures are important. That is another factor. So crystal structure is important, and then we talked about another thing, which is imperfections. Imperfections in the sample. Agree? You remember missing chairs. Imperfections in the sample. That determines the diffusion coefficient too. So then 5, concentration of the diffusing species. These are all important, okay? What are the factors that determines the diffusion coefficient? These are all important. And a very important application is the purification of hydrogen using palladium sheet. Okay, you know hydrogen is so important, right? Why? Aerospace engineers, you must know why hydrogen is important. Say, propellant, right? As a propellant, it's so important. So purification of hydrogen is very important, and that's where the palladium sheet can be used. You know, a palladium sheet is used. What happens is, in this case, you know, assume that this is again the chamber. You have that palladium sheet here, and your input or the inlet is, or the input through that inlet is impure hydrogen. Hydrogen contaminated with so many other impurities. And you allow that hydrogen to diffuse through that palladium sheet. What happens in that case is palladium allows only the pure hydrogen to pass through it. Okay? Depending on the nature. Remember, the structure of the crystal structure and the properties of that medium, it allows only pure hydrogen to pass through it. And on this side, what you get is purified hydrogen. Okay, purified hydrogen. That's the reason. You know, you adjust the pressure on this side and adjust the pressure on this side, so that when you input all the impure hydrogen into this side, and you get pure hydrogen from the other side. So that is the purification of hydrogen using palladium. So here is an example of a chemical protective clothing. So typically methylene chloride is a common ingredient of paint removers. Besides being an irritant, it also may be absorbed through skin. When using this paint remover, protective gloves should be worn. So what we are looking at is what should be the thickness of that protective gloves when you use this type of paints with that methylene chloride, okay, which is an ingredient in paint. So if butyl rubber gloves of thickness 0.04 centimeter are used, what is the diffusive flux of methylene chloride through the glove? And it is given like the diffusion coefficient in butyl rubber is equal to D is given, and surface concentrations are given. Okay, C1 and C2 are is given. So what is our equation? So D is okay. So that is the diffusivity is given here, and this is the exactly the thing. The gloves. So this is C1 and this is C2. This is the skin and this is the thickness of your gloves X1 and X2. So J is equal to, what is the equation? J is equal to minus D into dC over dx, and the x2 and x1 is also given, right? C2 and C1. If butyl gloves of 0.05 centimeter thick are used, what is the diffusive flux? 0.01. This is given. So this is equal to minus D into C2 minus C1 over X2 minus X1, and this is X2 minus D is given as D is equal to minus D is 110 into 10 to the power minus 8 centimeters square per second into C2 minus C1, which is C2, or we can, this is the difference, so you can 0.44 minus 0.02 over 0.04 centimeter, okay. This is 0. Grams grams per centimeter cube, and this is so 0.02, right, grams per centimeter cube. You can take this one as C2 minus C1. This is going to be, if you take C2 minus C1, it is going to be the 0.02 minus 0.044. Okay, you can take, if you want, you can take it in that case too. So if you take it like that one, the flux is going to be a positive. So you can take it in the other way. So into 0.02 minus 0.44 over 0.04 centimeter. So the value you get is 1.16 into 10 to the power minus 5 grams per centimeter square second. Okay, please take it as C2 minus C1. Okay, C2 minus C1, so you can get the value of flux in positive. This is going to be plus 1.16 into 10 to the power minus grams per centimeter square second. Yes.
So you say subtract the difference in numbers such that it'll produce a positive number, correct?
Yes, C2 minus C1. When you consider C2 minus C1, you know that's the reason why it is given in the equation. It is given as C2 minus C1. You know,
Okay.
J flux should be a positive value, so it's better to take it as C2 minus C1 itself.
Okay.
Okay. Now, the next one is non-steady state diffusion, and most of the diffusion are non-steady state diffusion. So, what is the meaning of steady state?
When
There is no accumulation or depletion of species within your material, within your medium. Okay, within your medium, when a steady state is reached. But in the case of, an important factor in that case, for in order to get that steady state diffusion, your thickness of the sample should be extremely thin, right? So remember, in the solid phase, this diffusion is a very slow process. In the gaseous phase, it's very fast. Liquid phase, it is faster. Not faster than gaseous, but faster than solids. But in solids, the diffusion is a very slow process. And this steady state can be reached only when you take that extremely very thin sheet of palladium or whatever that medium is. But in most of the other cases, it is not the steady state, it is the non-steady state diffusion. Which means the meaning of non-steady state diffusion is it is time independent. The steady state is time independent, whereas non-steady state is time dependent. Why? Because when you have a huge thickness or some thickness for your medium, the number of atoms diffusing through. For example, if you consider this as your diffusing medium, and the atoms are diffusing from this point to the other through this medium. So what does that mean? Because if you consider a point here, somewhere here, in 5 minutes, maybe you assume that 1,000 atoms diffuse through this point here. Okay? What happens in 10 minutes? You can see that maybe it is going to be 2,000 atoms or 3,000. I'm just putting some numbers there are diffusing through that point. After 1 hour, maybe 10,000. Agreed? That is called the non-steady state diffusion. Remember, it is a time-dependent diffusion. It is a no steady state is reached. So it is a time-dependent process. So this is the previously we have seen the Fick's first law. So there is the concentration is a function of both time and position. Concentration of the diffusing species, okay? Net accumulation or depletion. Diffusing species at different locations. So the diffusion flux and concentration gradient gradient varies with time. So you see, from here in terms of partial differential equation, we can write it as dou C. This is dou C means the partial concentration, dou C over dou T. Okay, this is just dou C over dou T is dou by x into d into dou C by dou x. This is from that fixed first law itself, but it varies with the time. That is the reason why you have that time factor here. Okay, so dou C by dou T is equal to dou over x into d into dou C by dou x. So, but if d is independent of composition, we can write it as dou C over dou T is equal to d into dou squared C over dou x squared. You know, this is from this equation. Dou C over dou T is equal to d into, that is the diffusion coefficient from here, into d into dou squared C over dou x squared. So this is the fixed second law. So the rate of change of concentration is equal to the product of d into diffusion coefficient into the change in the concentration gradient. Okay, so this is the rate of change, rate of compositional change is the product of d diffusion coefficient and the change of concentration gradient, d and change of concentration gradient. Okay, so that is the non-steady state diffusion and the fixed second law. And we will do a few problems as well as temperature dependence in the next class. Thank you.